Look up at the night sky tonight and let your eyes wander among those countless points of light. Each one is a sun like our own, some with planets circling them, whole worlds we may never know. The darkness between them isn't empty. It's alive with mysteries older than time itself. One of the greatest of those mysteries is cosmic inflation, the moment when our universe exploded from something smaller than an atom to something vast beyond imagining in less than the blink of an eye. Tonight, as you drift toward sleep, let's take a journey back to that impossible beginning, to the very edge of what science can explain. Picture yourself floating there, weightless in the darkness, as the universe whispers its oldest secrets. Where are you right now, curled up beneath this story? Is your window open to those same stars? Close your eyes and imagine them stretching back, not just across space, but across time, all the way to that first incredible burst of expansion. What we're about to explore isn't just science, it's the story of how emptiness became everything, how silence gave birth to galaxies, and how you are part of that grand unfolding. So breathe deep, let go of the day, and let the cosmos carry you into the deepest wonder of all, how we came to be here at all. Now, let's travel back to the very beginning, to a moment so small and so hot, it defies imagination. Picture a single point, tinier than the smallest speck you could ever see, yet holding within it all the energy and matter that would ever exist. This was the birth of the universe, a fiery explosion we call the Big Bang. In that first fraction of a second, temperatures soared beyond anything we can comprehend, trillions of times hotter than the core of our sun. Space itself was a seething ocean of particles, colliding, merging, and tearing apart in a frenzy of creation. But here's the mystery. Something extraordinary happened in those first moments. A force, still not fully understood, took hold of the universe and stretched it faster than light could chase it. Imagine blowing up a balloon, but instead of growing steadily, it inflates in an instant to the size of a city, then a planet, then a galaxy, all before you could even take a breath. This wasn't just expansion, this was cosmic inflation, a burst of growth so violent and sudden, it shaped everything that followed. What could possibly have caused such a thing? What kind of energy could bend the rules of physics so completely? The answer lies hidden in the fabric of space itself, in a field of energy so strange it turned emptiness into a powerhouse of creation. As you drift deeper into this story, remember every atom in your body, every star in the sky, traces back to this single, unimaginable moment. The universe was born in fire and stretched into existence by a force we're only beginning to understand. And the most astonishing part, this is just the beginning of the story. Now, let's unravel one of the universe's most puzzling mysteries, a question that left scientists scratching their heads for decades. Picture the night sky, vast and endless, dotted with galaxies so far apart they could never have touched. Yet, when we measure the temperature of the cosmic microwave background, the faint glow left over from the Big Bang, something strange emerges. No matter which direction we look, whether toward the edge of the observable universe or the opposite side, the temperature is almost identical, down to a tiny fraction of a degree. How could regions separated by billions of light years regions that could never have exchanged heat or information, be so perfectly matched. This is the horizon problem, a cosmic riddle that seemed impossible to solve. Without some connection, these distant corners of space should have developed wildly different temperatures over time, like two cups of coffee left in separate rooms, one cooling faster than the other. But the universe doesn't play by those rules. Instead, it whispers a story of harmony, as if everything was once intimately linked. This is where cosmic inflation steps in, offering a breathtaking solution. Imagine the universe in its earliest moments was small enough for every part to communicate, to share warmth and equilibrium. Then, in a flash, inflation stretched space so rapidly that these once close regions were flung apart, frozen in their matching temperatures before they could drift out of sync. It's like stretching a perfectly mixed blanket. The pattern stays the same, even as the fabric grows vast. Inflation didn't just solve the horizon problem, it revealed a deeper truth about the universe's infancy, a moment of unity that still echoes across the cosmos. And so, what seemed like a contradiction becomes a clue, a fingerprint of the universe's explosive birth. The harmony we see today isn't an accident. It's a relic of that fleeting instant when everything was connected before inflation carried it all apart. But the horizon problem isn't the only cosmic puzzle inflation helps us solve. Let's turn our attention to another mystery, one that deals with the very shape of the universe itself. Picture spacetime as a vast, infinite sheet. Now, imagine bending that sheet ever so slightly, creating a gentle curve. Over time, that curve should grow more pronounced, warping the fabric of the cosmos. Yet, when we measure the universe's geometry, something extraordinary emerges. It's perfectly flat, as if some unseen hand smoothed out every wrinkle. This is the flatness problem. According to the laws of physics, the universe's curvature should have become more obvious over billions of years. A tiny bend in spacetime early on would have magnified into something unmistakable, like a small crease in a piece of paper growing into a deep fold. Instead, what we observe is a universe so precisely balanced, it defies expectation. It's as if the cosmos is walking a tightrope, never tipping too far in any direction. Inflation offers an elegant explanation. Think of the universe in its earliest moments, a tiny speck filled with potential. If inflation stretched this speck exponentially in a fraction of a second, any initial curvature would have been smoothed out, just like stretching a crumpled sheet of rubber until it lies perfectly flat. The rapid expansion didn't just enlarge the universe, it ironed out its wrinkles, leaving behind the serene, flat expanse we see today. So, the flatness we observe isn't a coincidence. It's another clue, another whisper from the universe's first moments, telling us that something extraordinary happened. A burst of expansion, so powerful, it shaped the very fabric of reality. And just like that, what seemed like a cosmic oddity becomes a testament to inflation's transformative power. Now, let's unravel another cosmic enigma, one that involves particles so elusive, they seem to have vanished from the universe entirely. Imagine a magnet. You know it has a north and a south pole, right? Break it in half, and each piece still has both poles. But what if there were particles with just one magnetic pole, either north or south, never both? These hypothetical particles are called magnetic monopoles, and according to our best theories, they should be everywhere. Yet, despite decades of searching, we've never found a single one. This is the monopole mystery. In the early universe, conditions were so extreme that monopoles should have formed in abundance, like cosmic breadcrumbs scattered across space. They'd be relics of a time when the fundamental forces of nature were still merging into one. But here's the puzzle. If monopoles were as common as theory predicts, they'd be impossible to miss. Their sheer density would weigh down the universe, altering its evolution in ways we simply don't observe. So where did they all go? Cosmic inflation holds the key. Picture the universe before inflation, a hot, dense soup where monopoles were packed tightly together. Then, in a flash, inflation stretched space itself, spreading those particles so thin that they became incredibly rare. It's like taking a handful of sand and scattering it across an entire desert. Suddenly, what was once easy to find is now nearly impossible to spot. Inflation didn't destroy monopoles. It simply diluted them, hiding them in the vastness of the cosmos. So, the absence of monopoles isn't a flaw in our theories. It's another clue, another whisper from the universe's infancy, telling us that inflation didn't just shape space. It cleaned it up, leaving behind a cosmos where these strange particles are now needles in a galactic haystack. And just like that, a scientific puzzle transforms into a cosmic game of hide and seek, with inflation as the ultimate magician. Now, let's turn the page to a moment of pure cosmic inspiration, one that changed our understanding of the universe forever. Picture a young physicist named Alan Guth in the late 1970s, scribbling equations late into the night. Like many scientists of his time, he was wrestling with the same cosmic puzzles we've been exploring: the horizon problem, the flatness problem, and the mysterious absence of monopoles. But one evening, as he pored over his notes, something extraordinary clicked into place. Guth realized that if the early universe had experienced a burst of repulsive gravity, a kind of anti-gravity, it could stretch space faster than light itself. This wasn't just a wild idea. It was the missing piece that tied everything together. Imagine a balloon inflating so rapidly that every tiny wrinkle on its surface smooths out, or a cosmic reset button that stretched the universe from subatomic size to something vast in less than a blink. That's what Guth's insight proposed, a fleeting but colossal expansion that solved not one, but multiple mysteries in one elegant stroke. What's truly remarkable is how humble this revelation began. Guth wasn't in a grand observatory or a high-tech lab. He was working alone, piecing together ideas from particle physics and cosmology, when suddenly, the universe's secrets seemed to whisper back. His eureka, a moment, didn't just answer old questions. It opened entirely new ones, transforming inflation from a speculative idea into a cornerstone of modern cosmology. And so, Guth's breakthrough became more than just a theory. It was a triumph of curiosity, a reminder that sometimes the universe's greatest mysteries unravel in the quietest moments of thought. His story isn't just about equations or abstract concepts. It's about the thrill of discovery, the joy of seeing the cosmos in a way no one had before. And with that, the tale of cosmic inflation found its hero, not in a caped crusader, but in a physicist with a pencil, a notebook, and an idea that reshaped the universe as we know it. Now, let's step into the heart of cosmic inflation, the invisible force that made it all possible. Picture an energy field unlike anything we experience today, a kind of cosmic fuel that flooded the early universe. Scientists call this the inflation field, and for a fleeting moment, it was the most powerful thing in existence. Think of it like an engine running at full throttle, pushing space itself to expand at an unimaginable rate. This field wasn't made of matter or radiation. It was pure potential, a sort of cosmic tension woven into the fabric of reality. And just as a stretched rubber band snaps back when released, this field eventually lost its energy. But in that brief window, lasting maybe a fraction of a second, it did something extraordinary. It took the tiniest quantum jitters, fluctuations so small they'd normally vanish without a trace, and stretched them across the cosmos. Those minuscule ripples became the seeds for everything we see today: galaxies, stars, even the vast cosmic web, connecting them all. What's fascinating is how gentle this process was, despite its incredible power. The inflation field didn't tear the universe apart. Instead, it smoothed and stretched space like a master sculptor, shaping clay, turning chaos into order. And when its work was done, the energy stored in this field didn't just vanish. It transformed, reheating the universe into the fiery soup of particles we recognize as the Big Bang's aftermath. So the next time you look up at the night sky, remember, those glittering stars and swirling galaxies owe their existence to this mysterious field, a hidden force, active for less than a blink, yet whose echoes still shape the cosmos billions of years later. It's a reminder that sometimes the universe's most profound changes happen quietly, hidden in the spaces between moments. Now, let's take a closer look at how something unimaginably small grew into the vast structures we see today. Those tiny quantum jitters we mentioned earlier, fluctuations so small they'd normally be lost in the noise, became the architects of the cosmos. Imagine a quiet whisper, so faint you'd barely notice it. But when cosmic inflation stretched space itself, that whisper was amplified across the universe, turning into a shout that shaped everything. Here's how it happened. In the early universe, particles and energy were constantly popping in and out of existence, a natural feature of quantum physics. These fleeting fluctuations were random, uneven. Some spots had slightly more energy, others slightly less. Under normal circumstances, these differences would cancel each other out, but inflation didn't play by normal rules. As space expanded faster than light, those tiny irregularities were stretched to enormous scales, frozen into the fabric of the universe like cosmic fingerprints. What's truly remarkable is that these imperfections weren't flaws, they were essential. The slightly denser regions pulled in more matter through gravity, while the emptier patches stayed sparse. Over billions of years, those dense spots became the seeds for galaxies, galaxy clusters, and the vast cosmic web we see today. Without those quantum whispers, the universe would have been smooth and featureless: no stars, no planets, no us. So the next time you gaze at the night sky, remember this: the grand tapestry of galaxies began as the faintest tremors in the quantum realm. A universe that could have been uniform and quiet instead became rich and structured, all because inflation took those microscopic ripples and stretched them into the blueprints of existence. It's a story of how the smallest things can grow into the largest if given the right conditions and the right cosmic push. But let's listen even closer, because those quantum whispers didn't just shape the universe visually. They also left behind an echo, a kind of cosmic soundtrack. When inflation stretched those tiny fluctuations, they didn't just become uneven patches of matter. They also created ripples in the very fabric of space, like sound waves traveling through the early universe. Picture this: a dense region pulls matter inward with gravity, but the heat and pressure of the hot, young universe push back, creating a rebound effect. This push and pull generated oscillations, actual sound waves, that traveled through the primordial plasma. These weren't sounds you could hear with your ears, of course. They were pressure waves, moving at nearly half the speed of light, compressing and rarefying the soup of particles in rhythmic pulses. Then, around 380,000 years after the Big Bang, the universe cooled enough for atoms to form, freeing light to travel unimpeded. That moment froze those sound waves in place, imprinting their patterns onto the cosmic microwave background, the afterglow of the Big Bang. Today, that faint radiation carries the faintest traces of those ancient vibrations, like grooves on a cosmic record. Scientists call these patterns baryon acoustic oscillations, and they're one of the most important clues we have about the early universe. The spacing between these ripples acts like a cosmic ruler, helping us measure the expansion of the universe with incredible precision. It's as if the universe left us a message in its own language, a lullaby of vibrations from the dawn of time. So those quantum fluctuations didn't just build the cosmos, they sang it into existence. And now, billions of years later, we're just beginning to decode the melody. Now, let's stretch our imaginations even further, because what if inflation never truly stopped? What if, while our universe settled into the calm expansion we see today, other regions of space-time continue to inflate at unimaginable speeds? This is the mind-bending idea of eternal inflation, a theory suggesting that the rapid expansion didn't just happen once, but may still be happening right now, far beyond the edges of our observable universe. Picture a vast cosmic ocean, bubbling with new universes. In this scenario, inflation isn't a single event, but an endless process. Wherever the inflation field still holds enough energy, space-time keeps stretching exponentially, creating pockets where inflation eventually ends, each one becoming its own separate universe, with its own unique laws of physics. Our universe could be just one bubble in an infinite froth of cosmic realms, each born from the same unstoppable expansion. Some of these bubble universes might be eerily similar to ours, while others could be wildly different places where gravity is stronger, where time flows backward, or where matter never even formed. The multiverse becomes a cosmic patchwork quilt, stitched together by the endless creativity of inflation. And here's the most humbling part: we'll never see these other universes directly. The space between them inflates faster than light can cross it, leaving each bubble forever isolated, like islands drifting apart in an ever-growing sea. Yet, even if we can't visit these other worlds, the idea of eternal inflation reshapes how we see our own existence. It suggests that the conditions we take for granted, the perfect balance of forces that allowed stars, planets, and life to form, might not be a grand cosmic accident, but just one possibility among countless others. A soothing thought, isn't it, that somewhere out there, in the infinite expanse of the multiverse, every cosmic story you could imagine might be unfolding in its own way. And with that, we're left gazing into the cosmic dark, wondering what other mysteries inflation might still be hiding. Now, let's take this idea one step deeper, into the heart of the multiverse itself. If eternal inflation is real, then our universe isn't just a solitary bubble in the cosmic foam. It's one of countless others, each born from the same explosive expansion, but shaped by entirely different rules. Imagine a tapestry woven from infinite threads, where every stitch represents a universe with its own unique physics. Some might have stronger gravity, making stars burn out in an instant. Others could have no gravity at all, leaving matter to drift like fog in an endless void. There might even be universes where time runs backward, or where space has extra dimensions we can't begin to picture. This isn't just science fiction, it's a serious possibility within the framework of cosmic inflation. The same quantum fluctuations that seeded galaxies in our universe could, in other bubbles, have created entirely different structures. Some universes might be lifeless, filled with nothing but radiation. Others could be so alien that even the laws of cause and effect don't apply. And here's the wildest part. Because these bubbles are forever separated by inflating space, we'll never know for sure what's out there. The multiverse remains a breathtaking idea, hidden just beyond the edge of what we can observe. Yet, this hypothesis isn't just about cosmic variety. It might also explain why our universe seems so finely tuned for life. If every possible set of physical laws exists somewhere, then it's no surprise we find ourselves in a bubble where conditions are just right. The multiverse turns what looks like cosmic luck into a matter of probability. A comforting thought, really, that even if our universe is rare, it's not alone. Out there, in the infinite froth of creation, every possible reality might be unfolding in its own way, each a unique chapter in the grand story of inflation. And as we ponder this, the cosmos feels less like a single stage and more like an endless theater, where the curtain never falls on the show of existence. Now, let's turn our gaze from the multiverse's infinite possibilities back to our own universe, where scientists are hard at work, hunting for the fingerprints of cosmic inflation. The key to unlocking this mystery lies in the oldest light we can see, the cosmic microwave background, a faint glow left over from the universe's infancy. Think of it as a baby picture of the cosmos, imprinted with clues about its explosive beginnings. One of the most promising clues comes from a subtle feature called B modes, a specific pattern of polarized light woven into this ancient radiation. These patterns are like ripples on a pond, created when inflation's violent expansion sent gravitational waves surging through space-time. If we can spot them, they'd be direct evidence that inflation really happened, a smoking gun, from the universe's first moments. But finding these whispers from the dawn of time isn't easy. Scientists use powerful telescopes, stationed in some of Earth's most remote places, from the icy plains of Antarctica to the thin air of high-altitude deserts. These instruments scan the sky with incredible precision, separating the faint signal of B modes from the cosmic noise of dust and galaxies. It's a painstaking process, like listening for a single note in a symphony of static. The stakes couldn't be higher. If B modes are detected, they'd confirm not just inflation, but also the quantum nature of gravity itself, tying together two of physics' greatest puzzles. Yet, the universe loves a challenge. So far, these elusive patterns have remained just out of reach, hidden behind cosmic dust and competing signals. But with every observation, we get closer to answering one of cosmology's biggest questions. Did our universe really begin with a burst of hyper-fast expansion? This isn't just about proving a theory, it's about peering into the very fabric of reality. And as the search continues, each new scan of the sky brings us one step closer to understanding how everything began. The hunt for B modes took a dramatic turn in 2014 when a team of scientists working with the BICEP 2 telescope made an announcement that sent shockwaves through the world of cosmology. They believed they had found the Holy Grail, the twisted patterns of primordial B modes etched into the cosmic microwave background. For a brief, exhilarating moment, it seemed like inflation's boldest prediction had been confirmed. Headlines declared a breakthrough, and the scientific community buzzed with excitement. This wasn't just data. It felt like a direct message from the universe's first trillionth of a second. But science has a way of keeping us humble. As other researchers scrutinized the findings, doubts began to emerge. Could the signal really be from inflation, or was something else mimicking it? The answer, it turned out, was written in the stars literally. Further analysis revealed that much of the signal came from cosmic dust within our own galaxy, tiny particles that scatter light in ways eerily similar to the predicted B modes. The initial euphoria gave way to sobering revision. What seemed like a triumph became a masterclass in the challenges of cosmic detective work. Yet, even in disappointment, there was progress. The BICEP 2 episode taught scientists valuable lessons about the complexities of interpreting such faint signals. It underscored the need for multiple lines of evidence and more precise instruments to separate inflation's whisper from the universe's background noise. And so, the search didn't end. It evolved. New collaborations formed, combining data from telescopes like Planck and future missions to peel back the layers of cosmic interference. This story isn't just about a near miss. It's a reminder that science advances through both triumphs and setbacks, each misstep sharpening our tools and refining our questions. The universe isn't giving up its secrets easily, but with every careful observation, we're learning to listen more closely to its ancient echoes. As the dust settled from the BICEP 2 controversy, the scientific community turned to another cosmic observer, the Planck satellite. Unlike the fleeting excitement of a single discovery, Planck's work was a marathon of precision, patiently mapping the cosmic microwave background with an eye for detail never before achieved. Imagine a cartographer sketching the faintest contours of a newborn universe, tracing every ripple and shadow left over from its explosive infancy. What Planck revealed was both groundbreaking and humbling. Its ultra-sensitive instruments measured temperature variations in the CMB with such accuracy that they could distinguish between competing theories of inflation. Some models were ruled out entirely, while others had to be tweaked to fit the new data. Yet, even with this wealth of information, Planck didn't hand scientists a definitive answer. Instead, it narrowed the possibilities, like a detective eliminating suspects, while the true culprit remains just out of reach. One of Planck's most fascinating contributions was its ability to measure the polarization of the CMB, the same subtle patterns Bicep 2 had hoped to detect. While it didn't find conclusive evidence of primordial B modes, it did something equally important. It mapped the cosmic dust that had mudded earlier observations. This was like cleaning a foggy window, giving future missions a clearer view of where to search next. The satellite's data also hinted at a few cosmic oddities, subtle anomalies in the CMB that don't quite fit our standard models. Some regions of the sky appear slightly colder or warmer than they should be, and the large-scale patterns aren't as uniform as inflation predicts. These quirks might be mere statistical flukes, or they could be whispers of something deeper, waiting for the next generation of telescopes to decipher. Planck's legacy isn't just in the answers it provided, but in the sharper questions it left behind. It showed us that the universe's baby pictures are more nuanced than we imagined, with details that both confirm and challenge our understanding of cosmic inflation. And as we continue to study these ancient echoes, one thing becomes clear. The story of the universe's birth is still being written, one precise measurement at a time. While Planck's findings refined our understanding of inflation, they also opened the door to other possibilities, alternative explanations for the universe's early moments that dare to imagine a different cosmic origin story. One such idea is the bouncing universe theory, which suggests our universe didn't begin with a bang, but with a rebound. Picture a cosmic yo-yo. Instead of exploding from nothing, the universe collapses and then springs back, cycling through endless expansions and contractions. This elegant twist removes the need for a singular starting point, offering a universe with no true beginning or end, just an eternal dance of collapse and rebirth. Then there's the variable speed of light theory, a bold reimagining of one of physics' most sacred constants. What if light didn't always travel at its current speed? In the early universe, light might have raced faster, allowing distant regions to communicate and synchronize without inflation's rapid expansion. It's like rewinding a film and changing the rules, adjusting one fundamental parameter to solve the same cosmic puzzles in a completely different way. Some theories even blend quantum gravity with cosmology, proposing that spacetime itself has a granular, pixel-like structure at the tiniest scales. In these models, the smooth expansion we call inflation might be the emergent effect of deeper, more chaotic quantum processes, like watching the ripples on a pond without seeing the raindrops that created them. Of course, these alternatives aren't without their own challenges. The bouncing universe must explain what triggers the rebound, while variable light speed theories struggle to fit with our well-tested understanding of relativity. Yet their very existence is a reminder that science thrives on questioning. Even the most elegant ideas, like inflation, must earn their place by surviving every challenge. What's fascinating is how these competing visions share a common goal: to explain the same cosmic clues, the flatness, the uniformity, the absence of monopoles, but from entirely different starting points. It's as if detectives are solving the same mystery with completely different sets of fingerprints. And as future experiments probe deeper into the universe's first moments, we may yet find that the truth lies somewhere between these ideas, or in a theory no one has imagined yet. So while inflation remains the leading explanation, these alternatives keep the story exciting, reminding us that the universe's beginnings are still a puzzle with many possible pieces. And that's the beauty of cosmology. Every unanswered question is an invitation to dream bigger. Now, let's turn our attention to one of inflation's most delicate moments: the graceful exit. Imagine a cosmic tightrope walk where the universe had to step off the stage of rapid expansion at just the right moment. Too soon, and the universe wouldn't have stretched enough to solve the horizon and flatness problems. Too late, and space would have been stretched so thin that matter could never clump together to form galaxies, stars, or planets. It's a Goldilocks scenario where timing was everything. This transition wasn't just a simple flick of a switch. The inflation field, that mysterious energy driving the expansion, had to decay in a very specific way. Think of it like a pot of water boiling over, except instead of water, it's the fabric of space-time itself. As the field's energy transformed, it released a burst of particles and radiation, reheating the universe in what we often call the true Big Bang. But here's the catch: if that decay had been uneven or chaotic, the universe would have ended up lumpy or fragmented, with regions expanding forever while others collapsed. Instead, it unfolded with remarkable precision, leaving behind the smooth, balanced cosmos we see today. What's even more fascinating is how this moment connects to us. If inflation hadn't ended just right, the quantum fluctuations that seeded galaxies might have been too weak or too strong. Too weak, and the universe would be a dark, empty void. Too strong, and matter would have clumped into black holes long before life could emerge. It's as if the universe had to thread a needle, a single misstep, and we wouldn't be here to ponder it. This delicate balance raises a profound question. Was this perfect timing just a cosmic accident, or does it hint at deeper laws we've yet to uncover? Some theories suggest the inflation field had built-in mechanisms to ensure a smooth exit, like a self-correcting engine. Others wonder if multiple universes exist, each with its own exit story, and we simply live in the one where everything aligned. Whatever the answer, the graceful exit reminds us that our universe is a masterpiece of precision. From the tiniest quantum flicker to the vast cosmic web, every step had to be just right. And that's the next chapter of our story, how this reheating moment set the stage for everything that followed. Now, let's step into the fiery aftermath of inflation, the moment the universe woke up from its rapid expansion and burst into life. Picture this: the inflation field, that invisible force stretching space, finally begins to lose its grip. As its energy unravels, it doesn't just fade quietly. Instead, it explodes into a searing storm of particles and radiation, like a dormant volcano erupting after centuries of silence. This is reheating. the universe's true Big Bang, where emptiness became abundance in a flash of cosmic alchemy. For a fraction of a second, the cosmos was a churning cauldron of energy, hotter than the core of any star. Quarks, electrons, and photons, the building blocks of everything we know, sizzled into existence, colliding and combining in a frenzied dance. It's as if the universe hit a reset button, trading the cold, stretched emptiness of inflation for a blazing, particle-filled dawn. This wasn't just a transformation, it was a rebirth. The moment the universe became tangible, something more than just expanding space. What's astonishing is how this chaos birthed order. Those tiny quantum fluctuations, stretched to cosmic scales during inflation, now served as blueprints. Slightly denser regions began pulling in matter, like invisible hands gathering stardust. Over billions of years, these specks would grow into galaxies, stars, and planets. But none of it could have happened without reheating's perfect storm. Too little energy, and particles would have drifted apart, leaving the universe dark and lifeless. Too much, and the violence would have torn everything apart before structure could form. Yet here's the warmth in this cosmic tale. Reheating didn't just fill the universe with stuff, it filled it with potential. Every atom in your body, every star in the sky, traces back to this explosive moment. It's a reminder that creation isn't always gentle. Sometimes it takes a cataclysm to set the stage for beauty. And as the universe cooled, that energy began weaving the story we're still part of today, a story that, against all odds, led to us. Now, let's fast forward through billions of years to another cosmic mystery, unfolding right now: dark energy. If inflation was the universe's explosive first breath, dark energy is its slow, steady exhale, stretching space in a way that eerily echoes those early moments. But here's the twist. While inflation was a fleeting burst, dark energy seems to be here to stay, pushing galaxies apart at an ever-increasing pace. Think of it like two bookends holding up cosmic history. On one end, inflation, a violent, ultra-fast expansion that lasted less than a blink of an eye, sculpting the universe's structure. On the other, dark energy, a gentle but relentless force that's been accelerating the universe's expansion for billions of years, pulling galaxies away from each other like invisible hands. Both are invisible, both defy simple explanation, and both remind us how little we truly understand about the fabric of reality. What makes dark energy so puzzling is how different it behaves from inflation. Inflation's energy field faded, transforming into the matter and radiation we know today. But dark energy, it appears to be constant, as if woven into space itself. Some theories suggest it's the energy of empty space, a concept so strange it challenges our very understanding of physics. Others wonder if dark energy might change over time, just as inflation did, hinting at even deeper layers of cosmic mystery waiting to be uncovered. Yet despite their differences, these two forces share a profound connection. Without inflation, the universe would never have had the structure to form galaxies, stars, or planets. Without dark energy, the cosmos might have collapsed long ago, or expanded too slowly for life to emerge. Together, they frame the story of our universe, one setting the stage, the other shaping its fate. And here's the humbling thought. We're caught between these two mysteries, living in the brief sliver of cosmic time where the universe is neither too hot nor too empty, but just right for us to exist. It's as if the cosmos conspired to create a window, a fleeting moment in its grand timeline where beings like us could look up, wonder, and piece together this extraordinary tale. Now, let's venture into the realm of string theory, where the mysteries of cosmic inflation might find their deepest explanation. Imagine the universe not just as the three dimensions we know, but as a cosmic symphony of tiny, vibrating strings, each note playing out in hidden dimensions beyond our perception. This is the world string theory paints, and it could hold the key to understanding inflation's driving force. At its heart, string theory suggests that everything in the universe, from the tiniest particle to the vastest galaxy, is made up of unimaginably small strings. These strings vibrate at different frequencies, much like the strings of a violin, creating the variety of matter and energy we see around us. But here's where it gets fascinating. These strings don't just dance in the three dimensions we're familiar with. They move through as many as 10 or 11 dimensions, most of them curled up so tightly we'd never notice them. So how does this connect to cosmic inflation? Picture the inflation field, that mysterious energy that stretched the universe in its earliest moments. As one of these vibrating strings, some theories propose that the inflation field could be tied to a higher dimensional string, its vibrations unleashing the repulsive gravity that drove the universe's explosive expansion. It's as if the universe's first breath was a note played on a cosmic string, resonating through hidden dimensions. Even more intriguing is the idea that these extra dimensions might explain why inflation ended so abruptly. Just as a guitar string settles after being plucked, the higher dimensional strings responsible for inflation could have relaxed, their energy transforming into the matter and radiation that filled the young universe. This would weave inflation seamlessly into the larger tapestry of string theory, linking the universe's birth to the fundamental fabric of reality itself. Of course, string theory remains unproven, a beautiful but elusive framework that stretches our imagination to its limits. Yet if it's correct, it could reveal that inflation wasn't just a random event. It was a vibration in the deepest layer of existence, a ripple in the multidimensional symphony of strings that compose our cosmos. And that's a thought worth drifting off to as we ponder the hidden harmonies of the universe. Now, let's turn our gaze to one of the most puzzling questions in cosmology, the measure problem. Imagine standing in a universe so vast that every possible outcome, every alternate reality, exists somewhere within it, in an infinite multiverse spawned by eternal inflation. How do we even begin to calculate probabilities? If every conceivable event happens an infinite number of times, what does likely or unlikely even mean? This is the heart of the measure problem. Think of it like trying to count grains of sand on an endless beach. No matter how many you tally, there's always an infinite number left, making it impossible to say which type of grain is more common. In the multiverse, where countless bubble universes bloom with different laws of physics, how do we determine the odds of finding ourselves in a universe like ours, one with stable atoms, habitable planets, and the conditions for life? Some theorists suggest we might need a cosmic ruler to compare infinities, a way to slice the multiverse into measurable chunks. Others propose that observers like us inevitably find ourselves in the rare bubbles where life is possible, an idea known as the anthropic principle. But even this raises deeper questions. If every possible universe exists, does that mean there are realms where the laws of physics shift unpredictably, or where time flows backward? The measure problem doesn't just challenge our math, it nudges us toward profound philosophical territory. In a cosmos where everything happens, does probability lose its meaning? Or does it simply remind us that our human-scale logic might be too small to grasp the universe's true nature? As we drift through these thoughts, remember, the measure problem isn't just a puzzle for physicists. It's an invitation to wonder about our place in the multiverse, the nature of reality, and whether the very idea of chance might be far stranger than we ever imagined. Now, let's peer into the cosmic shadows where the secrets of inflation may still linger, waiting to be uncovered. While the echoes of the universe's explosive birth have faded over billions of years, faint traces of that primordial expansion might still be detectable if we know where to look. One promising clue lies in gravitational waves, the ripples in space-time first predicted by Einstein. These waves, created by violent cosmic events like colliding black holes, could also carry whispers from inflation itself. During that unimaginably rapid expansion, space-time would have been shaken by quantum fluctuations, generating a faint background hum of gravitational waves. Future observatories, like the Laser Interferometer Space Antenna, or LISA, may one day tune into this cosmic symphony, revealing patterns that only inflation could have produced. Another window into inflation's past could come from the farthest edges of the observable universe. The first galaxies, born in the wake of inflation, hold imprints of those early quantum seeds. Telescopes like the James Webb Space Telescope are already gazing deeper into space and further back in time than ever before. By studying the arrangement and composition of these ancient galaxies, scientists might uncover subtle fingerprints left by inflation's stretching of spacetime. Even the cosmic microwave background, that afterglow of the Big Bang, could still hide surprises. Tiny twists in its polarization, known as B modes, might carry the signature of gravitational waves from inflation's final moments. Though earlier searches were clouded by cosmic dust, next-generation experiments with sharper eyes could finally spot these elusive patterns. The beauty of these cosmic shadows is that they remind us how much remains to be discovered. Inflation may have ended in a blink, but its echoes could still be out there, etched into the fabric of the universe. As our tools grow sharper and our vision stretches further, we might one day glimpse those hidden traces, and in doing so, unlock the full story of how our universe began. And as we ponder these future discoveries, let's turn our thoughts to another profound idea: how our very existence might be intertwined with the rare conditions inflation created. But that's a story for another moment. Now, let's consider a thought that ties our existence to the grand cosmic drama of inflation. The anthropic principle suggests that the very fact we're here to ponder the universe means we must live in one of those rare pockets where conditions aligned perfectly for life. Imagine a vast multiverse, an endless sea of bubble universes, each with its own unique physics. Most might be too chaotic, too cold, or too unstable for anything resembling life to emerge. But in a handful, perhaps just one inflation, stretched spacetime just right, leaving behind a universe finely tuned for stars, planets, and ultimately, us. This idea isn't about claiming we're special in a mystical sense, but rather recognizing how the laws of physics in our universe appear oddly suited for life because, well, we couldn't exist otherwise. If the strength of gravity were slightly stronger, stars would burn out too quickly. If the cosmic expansion rate were faster, matter would never have clumped into galaxies. Inflation's delicate balance gave us a cosmos where these constants fell into place. Like a cosmic lottery, we somehow won. It's a humbling perspective, one that turns the question, why is our universe like this, into what other universes might be out there, unseen and unlivable. Some scientists even suggest that the multiverse could be a natural consequence of eternal inflation, with countless bubbles where the rules of reality play out differently. In most, life might be impossible, but here, in this quiet corner of the cosmic tapestry, we find ourselves in a universe that whispers, "Welcome home." And as we reflect on this delicate balance, let's turn our gaze outward once more to how these grand ideas have inspired not just science, but art, stories, and the very way we see our place in the cosmos. Now, let's step beyond the equations and telescopes to see how cosmic inflation has sparked the human imagination in unexpected ways. Science doesn't just live in labs and textbooks. It weaves itself into the stories we tell, the music we create, and the art that moves us. The idea of a universe bursting into existence, stretching faster than light, has become a muse for creators across the world. Take music, for example. Composers have translated the drama of inflation into soundscapes, swelling orchestral pieces that mimic the exponential expansion of space-time, or electronic tracks that pulse with the rhythm of quantum fluctuations. Some artists even use data from the cosmic microwave background as musical notes, turning the universe's oldest light into melodies. It's as if the cosmos itself is singing its origin story. Literature, too, has embraced inflation's grand narrative. Science fiction writers imagine travelers hopping between bubble universes, each with its own bizarre physics. Poets compare the stretching of space-time to the expansion of human consciousness, finding metaphors for growth and transformation in the cosmic dance. Even children's books introduce the idea of an inflating universe, with playful illustrations of galaxies drifting apart like dots on a balloon. Visual artists, meanwhile, paint the unseen, rendering the inflationary epoch in vivid colors, with brushstrokes that evoke energy fields and quantum ripples. Installations use light and motion to simulate the universe's rapid expansion, inviting viewers to step inside the moment of creation. And in film, directors borrow inflation's imagery for scenes of cosmic birth, where the screen explodes with swirling galaxies born from primordial chaos. What's fascinating is how these creative works make the abstract tangible. They take a theory that deals with fractions of a second and scales beyond comprehension and grounded in something visceral, a song, a painting, a story. In doing so, they remind us that science and art are two sides of the same coin, both trying to make sense of the wonder around us. And as we see inflation reflected in culture, it becomes more than a scientific idea. It's a shared human story. One that connects the equations on a physicist's chalkboard to the chords of a symphony, the lines of a poem, or the colors on a canvas. It's proof that the universe's greatest mysteries don't just belong to scientists, they belong to all of us, whispering inspiration across disciplines and dreams. With this fusion of science and creativity in mind, let's turn to the voices who have questioned inflation's story, exploring how even the most elegant theories face scrutiny and debate. Yet even the most beautiful theories must stand up to questioning, and cosmic inflation is no exception. Some of the brightest minds in physics have raised thoughtful challenges, not to dismiss the idea, but to refine it, because that's how science grows. Take Paul Steinhardt, one of inflation's early architects, who later became one of its most vocal critics. He argues that while inflation solves certain puzzles, it creates others, like the multiverse problem. If inflation can spawn infinite universes with random properties, how do we test it? A theory that predicts everything, he suggests, risks explaining nothing. Then there's Roger Penrose, who offers a radically different vision. His conformal cyclic cosmology suggests the universe cycles through endless rebirths, with no need for inflation at all. To Penrose, the smoothness of the cosmos isn't from rapid expansion, but from the fading of previous eons, a poetic alternative that challenges inflation's dominance. Even among supporters, debates simmer. Some argue inflation has become too flexible, with countless versions tweaked to fit new data. Others point to the lack of direct evidence, like the elusive primordial gravitational waves that would seal the deal. These critiques aren't attacks, they're part of science's self-correcting heartbeat, ensuring no idea goes unchallenged. What's remarkable is how these dissenters engage. They don't reject inflation outright, but push for sharper questions, better tests. It's a reminder that cosmology, at its best, is a dialogue, a collective search for truth, where every voice, even the skeptical ones, moves us closer to understanding. And as we'll see next, that dialogue is far from over, with new experiments poised to weigh in on inflation's fate. But the conversation doesn't end with debate. It evolves with discovery. Right now, a new generation of telescopes and experiments is gearing up to test inflation's boldest predictions, bringing us closer than ever to answers. Leading the charge is the Cosmic Microwave Background Stage 4 project, or CMBS-4 for short. This ambitious global effort will map the afterglow of the Big Bang with unprecedented precision, hunting for the faint swirls in polarized light called B modes, the smoking gun of inflation's quantum origins. Meanwhile, gravitational wave detectors like the Laser Interferometer Space Antenna, or LISA, will listen for ripples in space-time from the universe's first moments. These waves, if found, could carry echoes of inflation's explosive growth, a direct signal from the dawn of time. And on the ground, telescopes like the Simons Observatory in Chile are already scanning the skies, their ultra-sensitive instruments peeling back layers of cosmic dust to reveal the universe's primordial blueprint. But perhaps the most exciting frontier lies in the unknown. Future missions may uncover entirely new clues, anomalies in the cosmic microwave background, unexpected patterns in galaxy distributions, or even relics from before the Big Bang. Each experiment is a detective sifting through cosmic evidence, and every piece of data could rewrite our story. What's clear is this: the next decade will be transformative. Whether inflation's predictions hold or new theories emerge, one thing is certain: we're on the brink of revelations that will reshape our understanding of the universe's first whispers. And as these tools turn their gaze skyward, they carry not just scientific curiosity, but humanity's timeless wonder about where we came from. Now, let's step back and marvel at the bigger picture, because cosmic inflation isn't just science, it's poetry written across the fabric of the universe. Imagine the Big Bang not as a single explosive moment, but as the opening act of an endless cosmic symphony. Inflation stretches that first note into a melody, transforming a fleeting instant into a grand, unfolding process. It's as if the universe took a deep breath and never stopped exhaling, weaving galaxies and stars into existence with every expansion. This theory turns our origin story into something alive, dynamic, a dance of energy and space-time where quantum whispers grow into galactic shouts. Think of those tiny fluctuations, no larger than a billionth of a centimeter, stretched by inflation into the vast cosmic web we see today. What was once randomness becomes destiny, as if the universe itself was an artist sketching with quantum uncertainty. And here's the beautiful paradox: the more we learn about inflation, the more it feels like science and wonder are holding hands. The equations describe a process so elegant, it's as if the universe solved its own mysteries before we even knew to ask the questions. Inflation doesn't just explain the cosmos, it elevates our place in it. Every atom in your body, every star in the sky, traces back to those amplified quantum ripples, making us part of a story written in the language of space-time. So when you look up at the night sky, remember, you're not just seeing distant lights, you're witnessing the aftermath of creation's grandest performance, a poem penned in the first trillionth of a second, still unfolding around us. And that's the true magic of inflation. It doesn't just tell us how the universe began, but invites us to see ourselves as part of its endless, beautiful becoming. Now, let's take a moment to bring this cosmic story closer to home, because inflation isn't just about distant galaxies or abstract physics. It's about you. Every atom in your body, every breath you take, carries the echoes of that primordial expansion. Think of it: the carbon in your cells, the iron in your blood, even the calcium in your bones. All of it was forged in stars, but they're ingredients. Those trace back to quantum fluctuations stretched by inflation. You're not just living in the universe, you're made of it, a walking, talking piece of cosmic history. Close your eyes and picture this: trillions of atoms in your body, each one a descendant of those tiny quantum ripples from the universe's first moments. The same forces that shaped galaxies also shaped you. That's the real magic of inflation. It doesn't just connect dots in the sky, it connects us all, threading every person, every planet, every star into a single, shimmering tapestry of existence. So the next time you feel small under the night sky, remember, you're not separate from the vastness above. You're part of its story, woven into the fabric of space-time itself. And in that realization, there's a quiet kind of awe, a sense of belonging to something infinitely grand. Now, let's gently shift our gaze inward and embark on a quiet journey through time and space. Picture yourself floating in the deepest darkness, where the universe is smaller than a single atom, a tiny spark of potential. Here, in this infinite moment before time, you feel the first tremors of inflation begin. A force beyond comprehension starts to stretch the fabric of reality itself, and you're riding its wave, gliding effortlessly as the cosmos unfurls around you. Watch as space expands faster than light, smoothing out like a vast, silent ocean. Quantum ripples, those tiny whispers of uncertainty, grow into gentle hills and valleys, the future homes of galaxies. Stars flicker into being like distant campfires, each one a beacon in the growing dark. You drift past swirling nebulae, their colors soft as watercolor, and watch as planets slowly gather in the warmth of newborn suns. The further you travel, the quieter it becomes. The universe stretches thinner, colder, but never lonely, because every atom, every star, every flicker of light is connected to you. You are the witness, the traveler, the silent guest at the greatest show in existence. Now, let your mind settle into this cosmic cradle. Feel the weightlessness of space, the hush of billions of years, the gentle pull of gravity like an old lullaby. As the universe grows around you, so does your breath, slow, steady, matching the rhythm of creation itself. And when you're ready, let the stars blur into a soft glow, the galaxies into a haze, until all that's left is the quiet hum of the cosmos, singing you towards sleep. Let's take a quiet moment to marvel at this cosmic story we've been tracing together. Isn't it remarkable how much we've uncovered about the universe's first moments, how inflation stretched space like invisible hands, how quantum whispers became galaxies, how a fleeting burst of expansion shaped everything we see. Yet for all these discoveries, the cosmos keeps its deepest secrets close. We still don't know what sparked inflation's engine, whether other bubble universes exist beyond our view, or why the numbers in nature's equations align so perfectly for life. And perhaps that's the most beautiful part, not just the answers we've found, but the questions that still linger like starlight in the dark. This mystery is what keeps science alive, what sends telescopes scanning the skies and physicists scribbling equations at midnight. It's the same wonder that made ancient storytellers point to the heavens and imagine gods weaving the stars, except now we trace those threads with mathematics and light. Every unanswered question is an invitation to look deeper, to stay curious, to remember that the universe isn't just something we observe, but something we're woven into. Every atom in your body was forged in those first explosive moments, stretched across time to become part of you. So as you drift towards sleep tonight, carry that thought with you. You're not just under the stars, you're made of them. And the same force that set galaxies spinning still hums quietly in your breath, your heartbeat, the space between your thoughts. The cosmos isn't finished telling its story, and neither are we. What a gift it is to wonder, to explore, to belong to something so vast and yet so intimately close. Now, let the mystery cradle you like the gentle dark between the stars, knowing that every question left unanswered is just tomorrow's discovery waiting to unfold. As we come to the end of this cosmic journey, let's take one last look at the incredible story we've unfolded together. Cosmic inflation. That brief but unimaginably powerful expansion shaped everything we know, from the tiniest quantum ripples to the vast web of galaxies. It solved mysteries like the universe's perfect flatness and the eerie uniformity of the cosmos, while leaving us with tantalizing questions about what came before and what lies beyond our observable universe. Yet the beauty of science lies not just in the answers we've found, but in the mysteries that remain. Each discovery peels back another layer, revealing new wonders to explore. The next generation of telescopes, the subtle whispers of gravitational waves, the untested theories waiting in the wings, all of them hold the promise of deepening our understanding of how the universe began and where it might be headed. So as you close your eyes tonight, let your mind drift among these cosmic wonders. Picture the universe stretching, evolving, and whispering its secrets across billions of years. Remember that you are part of this grand story, woven from stardust and shaped by forces older than time itself. May your dreams be as boundless as the cosmos, filled with curiosity and a sense of awe for the mysteries still waiting to be uncovered. Thank you for joining me on this journey through space and time. If you enjoyed exploring the secrets of cosmic inflation, don't forget to subscribe and hit the notification bell so you won't miss our next adventure into the wonders of the universe. Until then, may your nights be filled with starry dreams and cosmic wonder. Sleep well, fellow explorer.